Basics of fault protection. Power system protection is a branch of electrical engineering that deals with the prevention of damage to electrical power systems due to faults. Here are some basic concepts. Faults in power systems are abnormal conditions that disrupt the normal flow of electric current. They can be caused by various factors such as equipment failure, natural disasters, or human error. The most common types of faults are short circuits and open circuits. Protection zones. A power system is divided into several protection zones. Each zone is protected by a set of protective devices. If a fault occurs within a zone, only the protective devices within that zone will operate. Protective devices. These are devices that detect and isolate faults. Examples include fuses, circuit breakers, and relays. Relays play a crucial role in power system protection. They detect abnormal conditions, like overcurrent or overvoltage, and trigger circuit breakers to isolate the fault. Circuit breakers are devices that can automatically interrupt the flow of current in a circuit when a fault is detected. Coordination ensures that the protective device closest to the fault operates first, leaving the rest of the system undisturbed. Speed and sensitivity. The protection system must be fast to minimize equipment damage and maintain system stability. It must also be sensitive enough to detect even high-impedance faults. Dependability and security. Dependability is the certainty that the protection system will operate correctly for all faults it's designed to handle. Security is the certainty that the system will not operate incorrectly for any condition. Remember, the goal of power system protection is to detect and isolate faults as quickly as possible to prevent equipment damage, ensure personnel safety, and maintain the stability of the power system. Earth faults and consequences of earth faults. An earth fault, also known as a ground fault, occurs when there's an unintended connection between a live conductor, a part of the system that carries current under normal conditions, and the earth. This can happen due to various reasons such as the failure or puncture of an insulator, unusual loads on transmission lines causing them to break and fall to the ground, or damage to the insulation during installation. Consequences of earth faults. When an earth fault occurs, the electrical system gets short-circuited, and a large amount of short-circuit current flows through the system. This has several effects. Equipment damage. The huge current can damage electrical equipment that comes in contact with the loop of earth fault circuits. Power supply interruption. The fault interrupts the continuity of the power supply. Safety hazards. If the fault current returns through any electrical equipment, it can energize the equipment's housing at a dangerous voltage. This poses a risk of electrical shock to anyone who comes into contact with the energized equipment. Voltage drop. A large amount of current flowing to the earth can cause the voltage to drop, which can affect other loads and may cause the burning of the phase or line. Therefore, it's crucial to have protection measures in place, such as restricted earth fault protection, to detect and isolate earth faults as quickly as possible to prevent these consequences. Restricted earth fault protection is a type of differential protection that detects and limits the fault current in transformers. It is based on the principle that the residual currents in the transformer windings are different from the zero-sequence currents induced by external faults. By measuring these residual currents, a relay can sense if there is an internal fault within a restricted area of the transformer, and trip the circuit breaker to isolate the faulted winding. This way, the fault current is reduced and the transformer is protected from damage. Restricted earth fault protection can be applied to both delta and star connected windings, as long as there are current transformers, CTs, installed at both ends of the protective zone. The CTs measure the zero-sequence currents in each phase of the transformer and provide a reference voltage for comparison with the residual currents. The relay is connected in parallel with one of the CTs and operates only for internal faults within its sensing range. The relay must be very sensitive to detect small differences between residual and zero-sequence currents, which are caused by internal faults. Restricted earth fault protection is also known as unit earth fault protection or differential earth fault protection. It is specified by ANSI 64 REF standard. It can be implemented using various devices, such as micrologic trip units, GPA relays, or other types of relays that meet the requirements of ANSI 64 REF. Restricted earth fault protection is an important feature for ensuring reliable and safe operation of transformers in power systems. The difference between restricted earth fault protection and differential protection is that restricted earth fault protection is more sensitive to detect internal faults within a limited area of the transformer, while differential protection is more general and can detect any phase faults within the transformer. Restricted earth fault protection is based on the principle that the residual currents in the transformer windings are different from the zero-sequence currents induced by external faults, and by measuring these residual currents, a relay can sense if there is an internal fault within a restricted area of the transformer, and trip the circuit breaker to isolate the faulted winding. Differential protection is based on the principle that under healthy conditions and under through fault conditions, the current entering a zone and the current leaving the zone are equal in magnitude but opposite in direction, so they cancel out each other at the relay and the relay does not operate. However, during an internal fault, there is only current entering and no current leaving, so the balance is affected and the relay operates. Restricted earth fault protection can be applied to both delta and star connected windings, as long as there are current transformers, CTs, installed at both ends of the protective zone. The CTs measure the zero-sequence currents in each phase of the transformer and provide a reference voltage for comparison with the residual currents. The relay is connected in parallel with one of the CTs and operates only for internal faults within its sensing range. Differential protection can be applied to any type of winding configuration, as long as there are CTs or other devices that measure both currents entering and leaving each phase of the transformer. Restricted earth fault protection is also known as unit earth fault protection or differential earth fault protection. It is specified by ANSI 64 REF standard. Differential protection is also known as Mersey's circulating current principle or differential principle. It is specified by IEEE 69 standard. Both types of protection are important features for ensuring reliable and safe operation of transformers in power systems. Hope this answer helps you understand the difference between restricted earth fault protection and differential protection. Importance of restricted earth fault protection. Restricted earth fault protection, REFP, is a scheme that protects transformers and reactors from internal faults by sensing the difference between the residual currents measured at the neutral earthing point and at the three-phase output of the transformer. The residual currents are caused by the leakage of zero-sequence currents from the transformer windings, which are proportional to the fault current. The REFP scheme consists of an earth fault relay, which is connected in parallel with the neutral earthing point and in series with a stabilizing current. The relay operates only for internal faults within a restricted portion of the winding, which is determined by its sensitivity and setting. When an internal fault occurs, it induces a higher zero-sequence current than normal, which flows through the relay and trips the circuit breaker. This limits the fault current and disperses it away from the transformer. The importance of REFP lies in its ability to detect and prevent damage to transformers and reactors caused by internal faults near the neutral earthing point. Internal faults can occur due to insulation breakdown, mechanical stress, or external influences such as lightning or switching operations. These faults can result in overheating, melting, or short-circuiting of the transformer windings, which can lead to fire, explosion, or loss of load. Internal faults can also affect other equipment connected to the same transformer or reactor, such as generators, motors, or cables. REFP offers several advantages over other protection schemes for detecting internal faults near the neutral earthing point. Some of these advantages are: high sensitivity. REFP can detect small changes in zero-sequence currents due to internal faults within a restricted portion of the winding. This makes it more sensitive than other protection schemes that rely on phase differential elements or impedance transformers. Fast operation. REFP can respond quickly to internal faults within a restricted portion of the winding by tripping the circuit breaker before reaching its rated current setting. This reduces the risk of overloading or damaging other equipment connected to the same transformer or reactor. Minimal disruption. REFP does not affect other parts of the system that are not within its restricted portion of operation. It also does not require additional components such as phase differential elements or impedance transformers that may increase complexity and cost. Therefore, REFP is an important scheme for protecting transformers and reactors from internal faults near their neutral earthing point. It provides reliable and effective protection for electrical systems that use low-impedance, grounded systems. Benefits of Restricted Earth Fault Protection. Restricted Earth Fault Protection, REFP, offers several benefits in the context of power system protection. High sensitivity, REFP is designed to be very sensitive to faults. It can detect fault currents that are just 15% more than the rated winding current. This allows it to protect a restricted portion of the winding, hence the name Restricted Earth Fault Protection. Effective protection, REFP provides effective protection against earth faults, especially for faults near the neutral of a transformer or a generator. It's particularly valuable when the equipment is low impedance grounded, where other protection elements might be ineffective. Minimize damage. By quickly detecting and isolating faults, REFP helps minimize damage to power system equipment. This can save significant repair and replacement costs. Continuity of supply. By restricting the fault current, REFP helps maintain the continuity of the power supply. This is crucial for minimizing downtime in power systems. Simplicity. REFP doesn't require taking into account factors like tap changer, transformer ratio, or vector group. This simplicity allows for increased sensitivity and optimal protection in the event of ground faults. Safety. By limiting the fault current and dispersing it away from the transformer, REFP enhances the safety of the power system. Components of Restricted Earth Fault Protection. Restricted Earth Fault Protection, REFP, is a protection scheme that involves several key components. Current transformers, CTs. These are placed on each phase at the outgoing side of the winding, and their secondaries are connected in parallel. A single CT is also connected in the line connecting the transformer to the earth. The output of the CTs is equal to the zero-sequence current that flows in the line. Earth Fault Relay. This relay is placed in the residual part of the CTs. It gives the tripping command to the circuit breaker and hence restricts the fault current. The relay operates only for the internal faults within the protective zone. It is designed to sense the fault current, which is 15% more than that of the rated winding current. Stabilizing resistor. This is connected in series with the relay to avoid the magnetizing inrush current. Circuit breaker. This device interrupts the flow of current in the circuit when a fault is detected. These components work together to detect and isolate faults, protecting the transformer and maintaining the stability of the power system. Please note that the exact configuration may vary depending on the specific model of your REFP system and the configuration of your system. What is 87TE Restricted Earth Fault Protection? In order to grasp the essence and functionality of Restricted Earth Fault Protection, it is expedient to start with the function and the challenges of classic phase differential protection. The differential protection has the decisive advantage of absolute and definitive selectivity, since the protection area is determined by the installation locations of the current transformers. One of its main challenges is the consideration of undesired residual currents, which can drive the algorithm into underfunctioning and, above all, into overfunctioning. In the case of generator and line differential protection, these are initially trivial mismatches due to typical CT errors and the CT ratios themselves. It gets really exciting when it comes to differential protection for transformers, since a few other aspects have to be taken into account here. In the case of a two-winding transformer, the transformer has two different voltage levels and correspondingly different nominal currents. Accordingly, the transformation ratio of the transformer must be taken into account by the protection algorithm. Other undesired differential currents arise due to the vector group of the transformer, since the currents between the transformer sides are phase shifted by 30 degrees per group number. Before the advent of digital protection technology, the deviations mentioned were compensated for using so-called matching transformers. Today's generation of protection relays works digitally and uses numerical calculation. A calculation is usually based on the rated current of transformer side 1, with the secondary measured currents being converted into primary currents. All other adjustments, such as vector group, transformer ratio, star point direction of the current transformer and the transformation ratio of the transformer, are taken into account numerically. But that's not all. The different neutral point treatment between the high and low voltage sides is also of great relevance. Residual current elimination. The figure below shows a transformer arrangement with a YYND group. As soon as the star point of a transformer side is grounded and an external single-pole short circuit occurs, the classic differential protection system is no longer able to stabilize. The reason? The zero-sequence system is not transferred to the other side of the transformer due to the existing compensation winding. The single-pole short circuit on the low-voltage side thus appears as a three-pole fault on the high-voltage side. Here the numerical residual current elimination is carried out by the protection algorithm. From the two vectors of the high and low-voltage sides, that the zero-sequence system of its own transformer side is subtracted from each phase current. The zero-sequence system is generally calculated on the basis of the symmetrical components. In example, the zero-sequence current of the high-voltage side is IPO equals 0 and the zero-sequence current of the low-voltage side is ISO equals 1. We now subtract the zero-sequence current from the phase current vector. An unchanged vector results here for the primary side, since the zero-sequence system on the high-voltage side simply does not exist or is 0. The magic now happens on the secondary side. We also get the vector of the high-voltage side, since the secondary zero-sequence system has now been eliminated or numerically subtracted. If the algorithm now calculates the differential and stabilization values, a stable system reappears in the event of an external single-pole fault. The zero current was eliminated numerically. The elimination of the zero-sequence current was also carried out with appropriate matching transformers before digital technology was introduced. Why restricted earth fault? The figure below shows the basic structure of a ground fault differential protection. As we can see, the protection function requires 4 analog current inputs. The measured current of the neutral point is compared with the calculated zero-sequence current of the three-phase currents. We have shown the function here in blue and drawn it in as a separate protection relay. In practice, the EDIF function is combined with the classic phase differential protection in one device and a total of 7 current inputs are required. The advantages of restricted earth fault protection are obvious. There is no tap changer, transformer ratio, or vector group to be taken into account. The transformer typical stabilization features are omitted. This allows increased sensitivity to be achieved and the grounded star winding is optimally protected in the event of ground faults. The residual current elimination of the phase differential protection can also be omitted. For larger power transformers from 20 MVA upwards, the restricted earth fault protection should be mandatory. Example ABB RADHD relay. Features primary side fault sensitivity down to 2 to 5% of main CT rating, high-speed operation, 10 to 20 milliseconds, pure operation, not affected by CT saturation, trip or flag indication relay included. Application: the RADHD relay is used for providing a high-speed restricted earth fault protection for transformers and reactors. The relay is connected to a CT in the neutral point of the transformer and residually connected CTs in the phases. Applications are not limited by CT saturation for external or internal faults. The saturation voltage of the involved CTs must be at least twice the selected operating value of the RADHD relay, and CT ratio correction can normally not be accepted. A nonlinear resistor is used at the CT summation point to protect the CTs from high peak voltages during internal faults. A short circuit current often contains a DC component that is larger in one phase than in the other two. In most cases, this direct current, having a time constant of, for example, 10 to 300 milliseconds, causes the current transformer to become saturated, which means that it is not capable of transforming correctly either the AC or the DC component. A restricted earth fault relay would therefore, if no special measures were taken, sense an earth fault current that does not exist on the primary side. The RADHD relay therefore contains a filter circuit which will attenuate the DC component. Practical experience has shown that a relay setting, according to formula, is sufficient to secure correct relay operation even for the most extreme transient CT saturation.